Hi, everybody. This is Dr. Nigro with the Chemistry Notes Screencast. This screencast is part of my series from our first unit of the year, our Introduction to Chemistry unit. This screencast is going to focus on two of the fundamental laws of chemistry, the law of conservation of mass and the law of definite proportion. As part of the screencast, I'm going to talk a little bit about what those laws are, and then we're going to go through some practice problems that show you how to apply those laws. All right, so first, before we get started, a quick definition. All right, what is a scientific law? I feel like we talk about scientific theories a lot, and people really confuse those two terms, a law versus a theory. So let's start with what is a scientific law? Well, basically, it's a description of observable chemical behaviors in nature. Oops. And it really describes how something happens. All right. Now, if you want to know why something happens, that is the theory. That's what a theory does for you. It explains why something happens. They tend to be more qualitative, they describe things. A scientific law is more quantitative, it describes how something happens. And these usually are accompanied by some sort of formula or some math. All right. Now, we're going to look at two laws, and they both definitely have formulas associated with them. And we'll talk a little bit about how we can utilize that formula to complete problems that deal with these two laws. All right. So, first up, the law of conservation of mass. Now, most people have heard of the law of conservation of mass, all right? But it was discovered by a French scientist named Antoine Lavoisier, right? He basically was doing some experiments where he found that the mass before the reaction happened was not equaling the mass after, and he hypothesized that they were losing a product in the form of a gas that was escaping from his reaction setup. So he decided to try just putting a lid or enclosing his reaction so he could try to capture that other elusive product. And when he did that, he found that all of the mass that was present before the reaction was present after that reaction. And that led to the definition of the law of conservation of mass. What it really states is that mass cannot be created or destroyed within a process. All right. And that process can be a physical change or a chemical change. All right. That mass can only be transformed. All right. So if we're talking about a physical change, maybe we go from a solid to a liquid. The mass present at the solid state must also be present in the liquid state. If we're talking about a chemical change, all right, so any chemical reaction, then the mass of the reactants must equal the mass of those products. All right. So another way to think about this is you can't just make stuff up and you can't just get rid of stuff because it's inconvenient. All right. The law of conservation of mass tells us that we have to account for everything that we have to start with. It must be somewhere in those products. Okay. So, what does that mean in terms of mathematics? All right. Well, let's look at this problem. All right. A scientist wants to make a 180 grams of glucose. Glucose is made up of hydrogen, carbon, and oxygen atoms. All right. To make the glucose, he needs to react 72 grams of carbon and 12 grams of hydrogen, but he can't remember how much oxygen that he needs. Can you help him? How much oxygen does he need for this reaction? All right. So, what's really happening here in simple terms is that carbon is reacting with hydrogen and oxygen to form glucose. All right. So, what the law of conservation of mass tells us is that the total mass here on the reactant side of the reaction must equal the total mass here on the products side of the reaction. So with that in mind, if I have 72 grams of carbon and I have 12 grams of hydrogen, I must have some amount of oxygen that is going to equal that 120 grams of glucose that I am trying to make. All right, so you can see I have one unknown right here. All right. So by setting the two sides equal to each other, I'm going to be able to calculate that unknown value. All right. So these two, 72 and 12, add up to 84 grams plus my unknown. And that's going to be equal to 180 grams. When I subtract the 84 from both sides, I'm going to find that I need 96 grams of oxygen if I want to make the glucose that the scientist is trying to make. Okay, so again, conservation of mass, product mass equals the reactant mass. All right, let's move down a problem. In a different experiment, the scientist reacts 36 grams of carbon with 6 grams of hydrogen and 48 grams of oxygen. How much glucose will be produced? All right, so same idea as before. The carbon plus the hydrogen plus the oxygen is going to produce that glucose. So that means that the total mass here, these reactants, has to equal the total mass on that product side. All right, so we plug things in. So we have 36 grams of carbon, 6 grams of hydrogen, 48 grams of oxygen. If we add those up, we should calculate the grams of glucose. All right, so we add everything together, and apparently we're going to make 90 grams of glucose from this starting material. All right, we're not going to make any more because we don't have the mass to do that, and we're not going to make any less because we can't just destroy mass. It's got to be there somewhere. All right, now this last one's a little trickier. All right, later a second scientist comes along and wants to make 270 grams of glucose. How much of each component, each reactant, am I going to need? All right, now I know from problems 1 and 2 how much carbon I need for 180 grams of glucose, how much hydrogen for 180 grams, and how much oxygen. Or I know the carbon for 90 grams, the hydrogen for 90 grams, and the oxygen for 90 grams. I can use those to set up ratios. All right, now remember, ratios require that whatever's in the top of your ratio also match on the other side of the equal sign, and whatever's in the bottom also match what is on the other side of the equal sign. So I'm going to use the information in part 2. All right, so first I'm going to start with carbon. All right, so I know that I need 36 grams of carbon if I'm going to make 90 grams of glucose. That's what we learned from this problem here. All right, so that means there must be some amount that I need if I'm going to make 270 grams of glucose. All right, so don't forget, when you set ratios up like this, the easiest way to do the mathematics is cross multiplication. So I'm going to cross multiply these two. All right, so that means I'm going to have 36 times 270 equal to 90 times x. All right, if I multiply 36 and 270, I'm going to end up with 9,720 equals 90 times x. And then when I divide by 90, I find that if I have 260 grams of glucose that I'm trying to make, I'm going to need 108 grams of carbon for that to work. All right, now I'm going to repeat, but I'm going to look at hydrogen this time. All right, so I have 6 grams of hydrogen for every 90 grams of glucose. So I can calculate the amount of hydrogen if I scale up to 270 grams of glucose. So again, I'm going to cross multiply. All right, I'm not going to write all the math out this time, but I'm going to multiply 6 times 270 and then divide by 90. And I find that I'm going to need 18 grams of hydrogen if I want to make 270 grams of glucose. All right, now oxygen, you have two choices on what you want to do for this calculation. So two options. All right, option number one is going to be to do the exact same thing we just did, except we'll say 48 grams of oxygen for every 90 grams of glucose is equal to some amount of oxygen for every 270 grams of glucose. We're going to cross multiply again, multiplying 48 times 270, and then dividing that by 90. And we're going to find that we need 144 grams of oxygen for this calculation. All right. Your second choice here is to use the law of conservation of mass. I know that the carbon plus the hydrogen plus the oxygen has to equal the glucose. All right, so that means in this case, the 108 grams of carbon plus the 18 grams of hydrogen plus X has to equal 270 grams of glucose. So I have one unknown, that amount of oxygen. All right. So I find that I'll have 126 grams on this side plus my unknown equals 270 grams. And when I subtract both sides, I find that the amount of oxygen that I need is shockingly 144 grams, which is exactly what I found using the ratio method. All right. Either of those will work. It's up to you what you would like to do there. All right. But again, keep in mind that when we do these ratios, I had grams of hydrogen up top, grams of hydrogen up top, grams of glucose on the bottom, grams of glucose on the bottom. So whatever is in the numerator needs to be the same in terms of chemical quantity. Whatever is in the denominator needs to be the same. All right. So now we're going to move on to the second law. This law is not quite as straightforward, generally speaking, as the law of conservation of mass, but it makes a lot of sense. All right. So first, we're going to talk about what do we mean by the chemical formula. All right. Well, remember, formulas are things like H2O for water, NH3 for ammonia, C6H12O6 for sugar. All right. They're what tell us what is in that particular compound. It's basically like the recipe for that chemical compound. All right, the symbols are the elements within that compound, and the subscripts are the number of atoms within that particular compound. So the recipe, what the ingredients are, and the amount of each that you need. All right. The law of definite composition tells us that for a pure substance, it will always be made of the same elements in the same amounts. All right. And for the amounts, we tend to use percentage by mass for those amounts. All right. Which in turn help us define those subscripts. All right. So what does that really mean? It means that if you define a particular compound as water, it doesn't matter where you get the water. If it's water, it's going to have two hydrogens and one oxygen in every molecule. And by mass, that's around 88% oxygen and 12% hydrogen. If instead I hand you a compound and that compound is 90, I don't know, 4% oxygen and 6% hydrogen, that cannot be water. Water has to be 88% oxygen and 12% hydrogen. If it's a different set of percentages, it is a different compound. Definite composition means that those mass percentages define which compound you have. All right. So that definite composition was a clue for early scientists on whether they had a compound they'd already seen before because they matched in terms of their percentages or something completely new. All right. So being able to calculate and use percentages is going to be a very important part of understanding how to apply the law of definite composition. All right. So the percent composition of a compound lists the percentage of each element's mass within, well, I'll write that out, sorry, within the compound. All right. So the percentage by mass of each individual element within that particular compound's formula. All right. The formula for percent mass is straightforward. It is just like any other percentage. All right. We know that percent basically is part divided by whole times 100%. All right. Well, that's the same here. The percent mass is the mass of the part, which in this case is going to be the element that you are looking at, divided by the mass of the whole, which is going to be the compound. And then you multiply that by 100%. All right, so it's still a part divided by whole. It's just this is a specific application. So it's element divided by compound. All right. We're going to be able to calculate percent composition in two ways by time we get partway through the year. The first way, which we're going to do this time, is using experimental data. All right, so the problem will tell you the mass values that you need, and you'll use them in the formula to calculate that percent. All right, the other way is using the chemical formula itself. All right, once we've talked about the mole and molar mass, we'll talk about how to do this second way for percent composition. But today we're going to focus on experimental data, not data. Okay. So the problems look something like this. What is the percent composition of 12.01 grams of carbon in 44.01 grams of carbon dioxide? All right. So percent of carbon is going to be equal to the mass of carbon divided by the mass of carbon dioxide times 100%. That's what the formula tells us. All right. So here the percent carbon will be equal to 12.01 grams of carbon divided by 44.01 grams of carbon dioxide. Then we would multiply that by 100%, and we find that carbon is 27.3% of carbon dioxide by mass. So that is your percentage of carbon. All right, now the problem didn't ask it, but what if I wanted to know the percentage of oxygen? All right, because there are only two elements in this compound, the percentages have to equal 100. All right, so the percentage of oxygen would be equal to 100% minus 27.3%, which equals, I always have to do this, 7 to 7. 72.7%, and that is the percentage of oxygen. All right, let's move down to this problem. All right, 40.08 grams of calcium reacts with chlorine to form 110.98 grams of calcium chloride, the compound. What is the percent composition of calcium in this compound? So we're going to start there. All right, the percentage of calcium is going to be equal to the mass of calcium, 40.08 grams, divided by the whole, 110.98 grams. Calcium chloride has this formula. We're going to learn that too, just not quite yet, but you can believe me. All right, so if I take the 40.08, divide by 110.98, multiply by 100, I'm going to get 36.1% for the percentage of calcium within this compound. All right. Part B, what is the percent composition of chlorine in this compound? Well, since there's only two elements, I know that the rest of that 100% must be the chlorine. All right. So 36.1% subtracted from 100 is going to tell me the percentage of chlorine. So 63.9% of the compound is comprised of chlorine by mass. All right. Up next, what mass of chlorine must have reacted? Now, this is where remembering the law of conservation of mass makes this problem much, much easier. All right, I know that the calcium plus the chlorine give us that calcium chloride compound. And I know based on the law of conservation of mass, the total mass over here on the reactant side has to equal the total mass over here on the product side. All right, well, I know I have 40.08 grams of calcium. I don't know how much chlorine, and the whole thing has a mass of 110.98 grams. All right, so by using the law of conservation of mass, I can set up this equality. When I subtract the 40.08 from both sides, I end up with 70.9 grams for the mass of chlorine in my 110.98 grams. What law did I use? Conservation of mass. All right, one of the best laws out there. All right. So that's one type of problem where we calculate that percentage. All right. There's another type of problem which allows us to use these percentages to set up ratios and calculate mass values using those. All right. So when working percent composition problems, another type of problem will have us using ratios. All right. For the ratios, we need to be careful. We need to make sure the numbers on the top of our ratios are for elements and the numbers on the bottom are for the compound on both sides of the equal sign. All right. If you want to flip them and put the compound on top and the element on the bottom, that's fine too. They just need to match. I tend to do it the other way though. Element on top, compound on the bottom. All right. When we set up these ratios, we can put mass values in. We can put percentage values in, or we can use both, which we're going to see a couple of examples of. All right, so let's write a couple of examples for some ratios that we could do. All right, so what I could do is I could compare one of my reactants to my product. All right, I could say the mass of A divided by the mass of AC has to be equal to the percentage of A divided by the percentage of AC. That's one set of ratios I could set up. I could also compare the reactants to each other. I could say that the mass of A divided by the mass of C has to equal the percentage of A divided by the percentage of C. That's another option. Or I could take the other reactant and compare it to the product, where the mass of C divided by the mass of the product, AC, equals the percentage of C divided by the percentage of AC. So these are just a couple of the possibilities that we can utilize our ratios for. Now, when you choose what to do, you should have 3 of the 4 numbers in your ratio. If you do not, you may have to do another calculation first, either using the percentages or using the mass. All right, so we're going to look at a couple different examples. All right, but before we do that, I strongly suggest you carefully organize this information. I like to utilize the graphic organizer. I've got a couple here just so you can see what it looks like. You do not have to, all right, but they do help quite a bit. All right, in particular, they can help you recognize the ratios that you are going to need to solve the problem. All right, so let's start with this first problem. Sodium oxide is produced from the reaction of sodium and oxygen. If 9.2 grams of sodium reacts with 3.2 grams of oxygen, how many grams of oxygen will be needed to react with 65.2 grams of sodium? All right, so for this organizer, I always set up the rows. The first row for me is always the compound. All right, so in this case, it's some compound between sodium and oxygen. I'll just write a general formula. All right, and then my element rows are next. So one element is sodium and the other element is oxygen. Now for this problem, I have a bunch of mass. I don't have any percentages, so I make one column mass 1, the other column mass 2, and then I'm going to fill them in. So I know that I have 9.2 grams of sodium reacting with 3.2 grams of oxygen. It wants to know how many grams of oxygen will be needed to react with 65.2 grams of sodium. All right, so this is a ratio I didn't actually put up above, but let me go back and do that. We'll use orange. All right, so the mass of A1 divided by the mass of C1 has to equal the mass of A2 times divided by the mass of C2, where 1 is the first, whoops, set of values and 2 is the second set of values. All right, now back to my problem. If you look, you can see our ratios. They're right here. Here's one ratio and here is the other. I'm going to set those two equal to each other. All right, so 9.2 grams of sodium over 3.2 grams of oxygen has to equal 65.2 grams of sodium over some amount of oxygen, my unknown. All right, so I'm going to cross multiply just like I did before. I'm going to multiply 3.2 times 65.2, then divide by 9.2, and I'm going to find that I need 22.7 grams of oxygen to react with this amount of sodium. All right, now before I move on, I like to look at my answer and ask myself if this answer is reasonable. All right, I scaled up the amount of sodium compared to 9.2. So that means I'm going to need to scale up the amount of oxygen. And I have 22.7 is greater than 3.2. So that is a reasonable answer. All right, two more. All right, next, aluminum fluoride is 32.1% aluminum by mass. Calculate the mass of aluminum in a 12.22 gram sample of the aluminum fluoride. All right, so I come over to my organizer. My compound is aluminum fluoride. I'm just going to put AlF3 because I already know what the formula is. My elements are aluminum and fluorine. All right, now note that subscript doesn't affect my row. It's irrelevant. All right, now this problem has two pieces of information. One is percentage and one is mass. So I change my columns to percentage and mass. The compound is always 100%. All right. And then this particular compound is 32.1% aluminum by mass. Calculate the mass of aluminum in a 12.22 sample of the aluminum fluoride. So I have 12.22 grams of the aluminum fluoride, and I'm asked to find the amount of aluminum that must be there. So once again, here are our ratios, all right? 32.1% of aluminum in 100% of that compound has to be equal to an unknown mass of aluminum present in 12.22 grams of that compound. All right, now if you want, you could have left it just as it is. 100 over 32.1 equals 12.2 over X. It's going to work out the same way. We're going to cross multiply, multiplying 32.1 times 12.22, and then dividing it by 100. And we're going to find that we need 3.92 grams of aluminum if we're going to make 12.22 grams of aluminum fluoride. All right. We ask ourselves if this is reasonable. We have a whole versus a part. We're calculating the part. It should always be less than that whole. And it is 30.92 versus 12.22. All right, last one, as you could just see, my battery's about to die. Right here we have acetic acid. It's 53.3% oxygen, 40% carbon, and 6.7% hydrogen. If you have 24.5 grams of carbon, how much acetic acid can we make? All right, so our compound is acetic acid. It's comprised of oxygen, carbon, and hydrogen. All right, we have percentage values, 100% for that acetic acid. We have 53.3% Oxygen 40.0% carbon and 6.7% hydrogen. We're given 24.5 grams of carbon and asked to find our acetic acid. So we're going to use these values to set up our ratios. All right, so 40% carbon and 100% acetic acid has to be equal to 24.5 grams of carbon in some amount of acetic acid. All right, we're once again going to cross multiply. So 24.5 times 100 divided by 40 tells us that we are going to have 61.3 grams of my acetic acid if we have 24.5 grams of carbon. All right. Again, is this reasonable? We just calculated the whole, which should be greater than the part, which it is. All right. So these are the two fundamental laws that we will be dealing with. The law of conservation of mass, which tells us that mass must be conserved. It cannot be created or destroyed, only transformed, which means the mass before the process or reaction has to equal the mass after. And then the law of definite proportions, which tells us that once we define a compound, it always must contain the same elements in the same amounts by mass. All right. If you have any questions about how to use the mathematical aspects of these laws, please let me know.